When we estimate a population parameter from a sample statistic, we have to fatten our point estimate to a confidence interval to account for the random variability in the sampling process. What is a confidence interval? A level C confidence interval for a parameter has two parts: an interval calculated from the data, usually in the form of an estimate plus or minus a margin of error, and a confidence level C, which gives the probability that the interval will capture the true parameter in repeated samples. There are a few important issues of note concerning confidence intervals. A confidence interval is an interval calculated from sampled data by a process that is guaranteed to capture the true parameter in a known percentage of all samples. The confidence level is the success rate of the method that produces the interval. In social science research, it's standard practice to use a 95% confidence level. This is sufficient for making management decisions and/or policy or program recommendation. In high-stakes scientific or life-and-death medical research, a higher level of confidence is required. We do not know whether the 95% confidence interval from a particular sample is one of the 95% that captures the true parameter value or one of the unlucky 5% that miss it. How a confidence interval is calculated depends on the nature of the parameter. In this video, we will consider confidence intervals for a population mean and for a population proportion. Let's quickly review important terminology necessary for our discussion. The population in a statistical study is the entire group of individuals about whom we want information. A sample is the part of the population from which we actually collect raw data. A parameter is a fixed value that describes the population. In practice, we don't know the actual value of this number. A statistic is a number that describes the sample. The value of a statistic varies from sample to sample. We often use a sample statistic to estimate an unknown population parameter. It's also useful to review the notation we use for common parameters in statistics. We use a capital letter N for the number of individuals in a population, and we use a lowercase n for the number of individuals in a sample. We use a lowercase Greek mu for a population mean, and we use x bar for a sample mean. Using Greek letters for the population parameters is pretty standard. We use a lowercase Greek sigma for a population standard deviation and a lowercase s for a sample standard deviation. Note that mu is the Greek m and sigma is the Greek s. The Greek letter for p is pi, but since pi already has a widely known fixed value, we often use lowercase p for the population proportion and use p hat for a sample proportion. However, as we'll see, sometimes p means something else and we have to substitute another symbol for the population proportion. The process for computing confidence intervals actually requires some fairly unrealistic conditions. First, we need a simple random sample of size n with no issues of bias or non-response. This condition alone is virtually impossible to achieve in practice. Next, the variable we measure is perfectly normally distributed with a mean mu and a standard deviation of sigma. Finally, although we do not know the population mean mu, we do know the population standard deviation sigma. This condition is hardly ever satisfied in practice. So what do we do about these unrealistic requirements? Are there any workarounds? When your data don't come from a perfect SRS, or simple random sample, your conclusions may be challenged. Focus on the contextual issues of whether the data can be trusted as a basis for the conclusions drawn. Use your expertise in the context in which you're working in order to justify using your data. Outliers can have extreme effects on confidence intervals. You should search for outliers and try to correct or eliminate them before performing calculations. The underlying population may not be perfectly normal. If the sample size is large enough, weirdly, a sample size n greater than or equal to 40 is big enough, then the distribution of the mean will be close to normal even if the individual measurements are skewed. We typically do not know the population standard deviation sigma. We can approximate sigma using the sample standard deviation S. That is, sigma is approximately S. Remember, this is the reason we use the n-1 in the denominator when calculating S. The margin of error, what I refer to as the fattening up of the point estimate, only accounts for error inherent in the method of constructing the confidence interval. It does not account for structural errors in the sampling process due to bias or non-response or undercoverage. Now let's go over the formula for calculating a 95% confidence interval for a population mean. This is a one-sample confidence interval. Draw an SRS, simple random sample, of size n from a large population having an unknown mean mu. An approximate 95% confidence interval for mu is given by the formula shown. Notice that we take x bar and fatten it up by adding and subtracting a fudge factor of 2s over the square root of n. Let's consider an example for finding a confidence interval for a population mean. The medical director of a large company looks at the medical records of 72 executives. He finds that the mean systolic blood pressure of this sample is x bar equal 126.1, and the standard deviation is S equal 15.2. We want to find a 95% confidence interval for mu, the mean blood pressure of all executives in the company. For a solution, we can use the formula for the confidence interval for a mean. We plug in our given numbers and simplify. We can conclude with 95% confidence that the mean blood pressure of all executives is between 122.53 and 129.67. Remember that in today's technological world, we usually use software for statistical computing. Using a TI-84 Plus calculator, we can compute a t-interval for the population mean. Under the test menu of the stat function, we select t-interval. The interval can be calculated using either sample data or sample statistics. We were given the statistics in this problem, so we input x bar equal 126.1, s equal 15.2, and n equal 72. We choose our C level to be 0.95 or 95% and calculate. The output is shown in the last screenshot. The confidence interval is exactly the same as we got with our formula calculation. Now let's consider the calculation of a confidence interval for a population proportion. We draw an SRS of size n from a large population that contains an unknown proportion p of successes. Recall that we use p instead of the Greek letter pi for the population proportion. We let x denote the number of successes in the sample. Then the sample proportion of successes is p hat given by x divided by n. The formula for computing an approximate 95% confidence interval for the population proportion is given. Basically, we compute the interval by fattening p hat by adding and subtracting the right amount. Let's consider an example. The National AIDS Behavioral Surveys found that 170 of a sample of 2,673 adult heterosexuals had multiple partners in the last year. We want to find a 95% confidence interval for P, the proportion of all adult heterosexuals having multiple partners. First, we need to compute P hat by taking 170 divided by 2673, and we get approximately 0.0636. Then we use the formula and plug in p hat equals 0.0636, 1 minus p hat equals 0.9364, and n equals 2673. We simplify, probably using a calculator, to get the confidence interval from 0.0542 to 0.0730. We can conclude with 95% confidence that the percentage of adult heterosexuals who had multiple partners last year is between 5.4% and 7.3%. Using the TI-84 Plus calculator, we use a 1 proportion z interval to compute this 1 proportion confidence interval for P. We input x equals 170, n equals 2673, and choose the C level to be 0.95. Notice that the output screen gives the same confidence interval as before and computes p hat as well.